This video will give an introduction to titrations, which is another application of acid-base chemistry that we'll be looking at. And in the very beginning of this video, we're going to start with what's technically the end point of your titration, and we're going to talk about indicators. So I'm not going to ask you to pick an indicator for a titration, but you may find that in other situations you need to do this. So we should talk about it a little bit. First, by just starting out with what a pH indicator is, and it is a substance that changes color as its pH changes. And we use this to determine when we've hit the end of a titration, the specific identity of the molecule determines its color and its useful pH range. So as an example, I want to look at phenol red. And this molecule has a pKa of 7.6. It is a weak acid. And what we find for phenol red is that if you have a pH less than 6.6, the solution is clear to light yellow. Right around a pH of 7.6, you have a persistent yellow color. And at a pH greater than 8.6, the solution is red. So what I want you to notice and take away from the specific points that we have talked about is that the lower range to the upper range, this pH less than 6.6, we're looking at pKa minus 1. And at the greater than 8.6, it's a pKa plus 1. So this is the range through which an indicator will be useful to use. So the way that you choose an indicator is look at the expected pH at the end point of your titration and pick an indicator that will change color at the correct point. So what we do with these molecules is we use very small amounts, about 1 drop, to show exactly where the pH changes in a titration. So let's talk about what an actual titration is and what the setup looks like. Now, second semester Gen Chem Lab is just chock full of titrations, and they are an analytical method for determining the concentration of a solute by reaction with a standard solution. So something that is a standard solution, it means that you know the concentration. So this has a known concentration and is usually very well known. So when you do a titration experiment, usually the very first thing that you do is standardize your solution, which you run a bunch of trials, you calculate the concentration of your standard solution with some error appropriately indicated, and then you use that standard solution to titrate your unknown. So the setup for this, and you'll have to forgive my terrible drawings because I did not have the forethought to bring in a cute graphic of a titration. You will have usually an Erlenmeyer flask, and it'll have some solution in it. You'll obviously have it on your stir plate with a stir bar. And then you'll have this other piece of glassware. It's this long, skinny thing with a tip, and then it has a little, it's called a stopcock. It's just a little plastic turny thing that lets you adjust whether or not the solution is coming out of this long, skinny piece of glassware. And this is called a burette, not a burette. So it's a burette. And what we put in the burette, we call it the titrant. And this is our known solution. So the burette gets the solution where you know the concentration, and the flask gets the unknown. So this is what we call the analyte. And in this solution, we will put the indicator, or sometimes, if you're very lucky, you can just put a pH meter into the solution and measure the pH. That way, as your titration is being carried out. So what this looks like, we'll kind of set this up sort of problem-solving wise, which is exactly what you'll need for the mathematical part of this, and it's how you would do it practically in the lab. Let's do this in some kind of different color. You know the concentration of the titrant. So you will add titrant to your unknown until you get to whatever the end point is. From the concentration, you can get the number of moles of titrant that you added. And because you will know exactly how these react, it's usually a really simple acid-base reaction where it's a 1-to-1 mole ratio of titrant to analyte. You can use the stoichiometry here to get moles of analyte. And those moles of analyte, if you know the volume of solution you started with, you can get the concentration of the analyte. And sometimes you can even take this a step further. So a lot of cases, this is where you'll stop, is you just want the concentration of the analyte. Sometimes what you'll actually be reporting is the pH of that final solution. So if you have a concentration, you'll know whether or not it's an acid or a base, and you can proceed accordingly. You might take that analyte and calculate the Ka, which is something that we know how to do, also using the pH. Or you could even go a step further and calculate the molar mass. So these are all examples that we'll see in our practice or in the problem set. Or if you don't encounter them here, you will encounter them in lab. So this is the basic setup for everything. Now, what we most often do is calculate the pH at regular intervals in class, or in lab you measure it at regular intervals, and then create this plot that's called a titration curve. So I'm just going to give you a quick example here, and then we're going to look at specific shapes of titration curves in the next video when we talk about different types of titrations. So a titration curve is a plot of pH of the analyte solution throughout the experiment. So our y-axis is pH. Our x-axis is volume of titrant added. So we start at 0, which is just whatever gets marked off on here is going to be the pH of our starting material, our starting solution. And then as we go through and add the titrant, the pH will change. So one possibility is that our titration curve, well, I guess let me actually have these. We'll say 2, 4, 6, 8, 10, 12 for our pH markings. So if my titration curve looks something like this, this gives me so much information. We'll talk about the specific types of information in the middle of the curve, but hopefully one of the first things that you can pick out from this titration curve is that my starting material was an acid, right? My pH started out super low, and my titrant must be a base because my pH became more basic throughout. The specific shape of this might feel a little bit weird, but I definitely started with an acid. I clearly went through, I neutralized this at some point, right? Because my pH of 7 is about here. So I crossed a pH of 7. So I actually really did make a neutral solution in this case. And I ended up with something that was basic after I had reacted all of my analyte.